Hi guys, we are going to be working at solving some equations of complex number z over the complex numbers. And who can make sense of these fun jokes? Why can't we be together? Ooh, because it's too complex. And I love maths, because I know you do too. So, let's get to it. Here's our first one. We're going to solve a quadratic equation with real coefficients, just like this, real coefficients, and we're going to solve it using a general quadratic formula. Okay, so we substitute our values from the quadratic equation into the formula. Make sure you use brackets in this case, because that's good to keeping track of negatives when you're using this formula. And let's simplify our part in the middle under the square root, and we can see it's a negative, so we're going to have a square root of a negative number there. And we pull out our square root neg 1, and we simplify and we write that as I. So don't forget this here, I is the square root of negative 1, very important. Nice and easy. Let's keep going. What about another example? Again, we've got real coefficients in this quadratic equation. We're going to solve using general quadratic formula. So you substitute your values in the formula and we work at simplifying the terms. And again, we've got a negative, the square root of 80, and we want to simplify that third. And we pull out the square root of negative 1 and write as imaginary unit I. And we have this as our two solutions in third form. Okay, now let's have a look at a slightly different equation. Now we've got z squared plus 3 is equal to 0. This is also a quadratic equation, but it's got a single z term, and those ones can simply be transposed for z. So we subtract 3 to the other side, then we perform a square root. Don't forget the plus and minus. Now the square root of a negative, okay, this is an imaginary number, so we pull out the square root of neg 1 and write as imaginary unit I, and there's our solutions. Nice and easy, huh? Okay, but what about now if the term is not a real number but an imaginary constant term in the equation? Like this, we've got this plus 2i there. So now we're going to transpose for z. Then we're going to convert to polar form, apply Demoivre's theorem, and then equate the modulus of z and the argument of z. This is how we perform roots of a complex number. Okay, so now we've got z squared is equal to negative 2i. So now what we're going to do is essentially the square root of a negative 2i. So this is this polar form trick where we do our workings in polar form, and we can use Demoivre's theorem. So the polar number of unknown complex number z could be expressed like this. There's an unknown polar number with a modulus and an argument, and all that is being squared. And we want to also have the negative 2i in polar form, so let's go about converting that. So we need the modulus of that number, which is whole number 2, and the argument of a negative 2i. Well, if you examine an R-game diagram, we can identify the negative 2i down here on the negative imaginary axis, 2 units down. And if we measure the angle from the positive real down to that number, we can see that's 90 degrees in this clockwise direction, and that's a negative 90 degrees angle for the argument. So put that together, there's our polar form, 2 cis of negative 90 degrees. Let's apply Demoivre's theorem, and we square the modulus, and we have 2 multiples of the angle in the polar form of z, and it's equivalent to this polar number, 2 cis of negative 90. So now we want to go ahead and equate the parts. So the modulus are equivalent, and the arguments are equivalent. Okay, so we get root 2 as your modulus. And what's most important here is including all possible angles that are always land in that same position on a unit circle of down here at the -2 on the imaginary axes. Now we could rotate 360 degrees and end up on that exact same position. So any multiple rotation of 360 degrees always going to land us on that same position on the Argand diagram. And it doesn't matter what the angle is, it's what the position on that diagram in complex space that matters. Okay, divide by 2 and simplify this rule. And now we're expecting two solutions for a quadratic equation. So the two solutions are going to be when we look at the first revolution, which is when k is 0, and we get our -45 angle. And then when we rotate again, we get our next possible angle, k equals 1, of 135 degrees. And we can put that together to get our complex numbers, Z1 and Z2, as our solutions to this equation. And if possible, we want to be able to convert them conveniently to a Cartesian form, so we can expand out the cis function and evaluate. Okay. And then just simplify our Cartesian form by expanding to √2. And we get this as our Cartesian, nice convenient Cartesian form of our solution Z1 and Z2. Not bad, huh? So let's look at a slightly more challenging problem. Now this is again another quadratic equation, but we've got a complex term. We've got a real part plus an imaginary part. So again, let's transpose. So add the 2 to the other side and subtract the -2i to the other side. And again, convert to polar form. Including the 2 minus 2i, convert that to polar form, so we need the modulus. And we get a 2√2. And a convenient form of expressing this square root of 8 is 8 to the power of a half. And you might notice that if we express with rational powers all our roots, then we can simplify our overall power of our modulus later on. Let's also get our argument. So we can use this formula, the inverse tan of -2 on 2. Check where that position is in an Argand diagram. This is our complex number down here, 2 minus 2i. And you can see it's down in this fourth quadrant, rotating clockwise below the 0 baseline measure for angle. And it's a -45 degrees. So there it is. There's the polar form of 2 minus 2i. Apply Demoivre's theorem. And now let's equate our parts. The modulus is equivalent. Now this 2√2 is the same as an 8 to the power of a half. And let's do the square root of that. So overall we're going to get an 8 to the power of a quarter. And there's our rule for finding the overall argument of the solutions. Divide by 2 and simplify it. And we want to get two solutions for a quadratic equation. So when k equals 0, we get this first angle, -45 on 2 degrees. And when k equals 1, into this rule here, simplify 315, divide 2 degrees. Okay, now these aren't common angles. We know exact value surds off. So at this stage, we're just going to express them and keep the solutions in their polar form here. And if you're interested to know what's the Cartesian form of these numbers for the solutions, you can evaluate this in a CAS. Okay, fantastic. Let's look at our next one. Number 6. So 6 is now slightly different. This is z to the power of 3. Okay, now let's go about transposing our number. So we bring the terms, the real and the imaginary terms, to the other side. And our strategy is to convert both numbers to polar form. So let's get the polar form here. The modulus gives us an 8√2. And the argument, evaluating the inverse tan, is going to give us a negative 45-degree angle on the calculator, but locating the number on your R-gain diagram, you see it's over here in the second quadrant, negative 8 in the reals and positive 8 in the imaginary is the second quadrant angle, and that's 180 degrees apart from your 45, negative 45. So go ahead and correct this angle, add 180 degrees to get 135 degrees for your argument. Let's put it together. So there's the left-hand side with using Demois's theorem with the power on the modulus and the argument is equivalent to the polar form of this complex number here. And let's equate the parts. So a useful way of expressing our 8 root 2 is with rational powers. So we've got 8 times 2 to the power of a half, and then all to the power of a third when we've done the third root or the cube root of the right-hand side. And multiplying through now our power of a third to both parts inside the bracket, and we can simplify that to give 2 and the 6th root of number 2. So knowing some index laws are very useful to simplifying these numbers. And let's work out the arguments. So we've got 3 lots of angle eta equals 135 plus 360k. Now, we're going to get 3 solutions for solving a cubic equation. So each of the solutions is given by this little rule when we simplify. 3 divides evenly into both numbers. So our 3 solutions are going to be when k equals 0, k equals 1, and k equals 2. And we can substitute that into our rule and get these angles, 45 degrees, 165 degrees, 285 degrees. Put them all back together to write your solutions, Z1, 2, and Z3 in polar form, and we have these. Okay, and we can evaluate them on your CAS to see what they look like in Cartesian form. Not necessarily pretty surds, but nonetheless, this is a convenient way of presenting your answer. How are we doing? I think we're making great progress. Let's look at one more. Now, this here we can also focus on looking at higher powers, polynomial equations. So here we've got z to the 4 plus 16i is equal to 0. So the same strategy applies. We're going to transpose for z. And then we're going to convert the polar form. So let's do it a little quicker this time. What's the polar number of negative 16i? Well, that's down here on the negative imaginary axis of an R-gain diagram. And you can see it's a negative 90 degrees angle. So put it together, we've got a modulus of just a positive 16, cis of negative 90. And now let's equate the parts. So we've got this as our overall argument, overall modulus. The 4th root of 16 nicely goes down to whole number 2. And we've got this as our argument formula for our solutions. So simplify it down. We get a common factor of 2. And now we're expecting 4 solutions from this 4th degree polynomial. So our solutions are going to be when k equals 0, k equals 1, and k equals 2, and k equals 3. And let's substitute the rule and simplify to get our angles. Now, the next one, k equals 3, it's going to start to give us a pretty large angle. It's negative 45 plus 540 degrees divided 2. So we're now, seems like we're getting degrees heading outside the first revolution of our unit circle. But when we halve it, of course, it is not too big, 247.5 degrees, which is down here in this third quadrant. Later we're going to be looking at what's a better way of presenting these angles and what's called a principal argument domain. Okay, and we'll see that ranges from a negative 180 degrees to a positive 180 degrees, and we will look at converting our arguments within that domain in future examples. Put all your complex number solutions together with the modulus cis of the argument as your last line. There's all our solutions, and of course we can evaluate them on the CAS to get your Cartesian form of the numbers. Okay, and we're done. So, introducing the next problem, I'm going to leave this as a challenge for you, and we can review it in class next time. But as you can see now, we've got two terms in this quadratic equation. We've got the z squared term plus an 8z, and then we've got our imaginary unit. So the strategy here is to complete the square in z. Then we're going to start to transpose for z using inverse operations, bringing the imaginary unit 16i over to the other side through subtraction. And then we use we convert to polar form and apply Demois's theorem, just like we've have approached the problems previously. So think about that method and see if you can solve this example on your own. Same with exercise 9. It's also a similar approach. We've just got an extra term here, this real term, that you can simplify when you go about completing the square. All right, that's enough hints for now. Well done, everyone. Everyone's done a great job, and let's keep studying hard.